What we're watching is a sequencer. The sequencer can be built as shown on the breadboard if you wish, using the parts in the sequencer bag labeled S. Or you can wait and build it on the PCB, or do both. You can reuse your parts or ask me for a second baggie and build it both on a breadboard and by soldering on the PCB. Ultimately, of course, you do want to solder it so it can plug in to the Euro rack module. What the sequencer does is it turns on a series of voltages in sequence. Our sequencer has 8 voltages with 10 possible. And each voltage as it turns on lights up a green LED. That's just for visualization. It changes which LED lights up on a trigger from a clock. That clock is the 555 timer over here in astable mode. This is the 4017 decade counter that takes clock pulses, either from an external input or from the 555 timer, and it advances the voltage one step at a time. And on each voltage output, we have a voltage divider to determine the output voltage, and that's what's being displayed on the voltmeter up here. So you can see we're marching through voltages somewhere between 1 and 2.5 volts on each step, and the voltage is selected by, of course, the location of the potentiometer. Let's take a listen to it by running the output of the sequencer into the voltage-controlled oscillator. We'll start with the triangular waveform. Notice how the higher pitches, of course, are higher voltages. This is how the voltage-controlled oscillator works. Works just fine, of course, on the ramp output as well. And without changing the output voltages, I can change the pitch by using the coarse and fine settings. Notice, of course, the input voltages from the sequencer haven't changed. We can adjust the frequency of the sequencer by using a potentiometer on the 555 timer. This happens to be its slowest setting at the moment, so that you can see the voltages change. Those will start to wash out as I increase the speed. Of course, we can change the pitches of individual steps. Watch as I change the pitch on the first step. We'll raise it. There. Raise it some more. All right. Now, notice we have 8 beats. The decade counter chip has a reset, which normally resets after it's run through 10 full steps. We're only using the first 8. And what I'm going to show you is what happens if we want to run with a faster or a less complex pattern. And I do that by taking the reset, which is on this green wire, and is currently set to what would be the 9th output that doesn't actually fire a voltage, and I'll move it upstream a bit. First of all, if I pull it, now we just have 3 beats that repeat because I'm taking the 4th output when it triggers and using it to reset. Oops, pulled the wrong cable. Now we're getting the full sequence again. I'll stop it somewhere else. And occasionally when you're playing with CMOS chips on a breadboard, you need to reset. Or you just have a bad connection, and this is of course one of the reasons why we stick things on PCBs. And so without careful attention to making good connections, you certainly can end up with some faults. Okay, there we go. A 7-beat pattern. Let's try to pull it and pick up the last one. That gap at 0 volts is of course from the would be the 9th and 10th outputs, which aren't there, so the VCO simply records 0. Let's go back to our original configuration of a nice 8-beat pattern. All right, that's the sequencer. Let's look at building it. I'm now exploiting the linear modulation capability of the sequencer. We'll change the magnitude of the modulation. No modulation at all when the dial is over. Modulation can be heard on top of the default pitch. All right, enough for now.